Hello there, Mr. Sutton here, bringing you the IM3 Chapter 8 Quiz 2 Review Solutions on Probability. For this problem, we're picking a card at random from a standard deck of 52 cards, and we want the probability that our card is a red face card. So if we're asking for the theoretical probability of an event happening, we're essentially asking for the number of desirable outcomes divided by the total number of possible outcomes. So in this case, dealing with the total number of possible outcomes when you take a card from this deck, there's 52 outcomes, one for each of the cards. So our probability is going to be something over 52. Now, how many of these 52 cards are the ones we're looking for? Well, we want red face cards. So what are those? Well, red is the suit of diamonds or hearts. And face cards, those are jacks, kings, and queens. So we have the jack, king, and queen of hearts, and the jack, king, and queen of diamonds. That's a total of 6 desirable outcomes to go in our numerator. And then we just reduce our fraction as much as we can. So reducing by 2's here, we end up with 3 over 26. For this problem, we have a set of cards numbered 1 to 20 and randomly pick one. We want the probability that the number on our card is a multiple of 4. So just like our last problem, let's start by figuring out the total number of possible outcomes. And it looks like since we have cards numbered 1 through 20, there's 20 outcomes. So our answer is going to be something over 20, at least initially, if we don't reduce it. And now for desirable outcomes, we want to count up the multiples of 4 that we can get between 1 and 20. So the first multiple 4 is 4 itself. So that's 1. After that, we have 8, 12, 16, and 20 itself. So that's a grand total of 5 multiples of 4. And then if we reduce that, we have 1 over 4. For this problem, I'm randomly picking a marble out of a bag with 8 greens, 4 blues, 12 yellows, and 10 reds, and I want the probability that the marble is not green. So it's sometimes easier when you have one of these questions asking for a probability of something not happening to find the probability that something will happen and then subtract that from 100%. So in this case, I'm going to start kind of counterintuitively by finding the probability that a marble is going to be green. Now to do that, just like I always do, I'm going to find out the total number of possible outcomes, and that's just the total number of marbles I have to choose from. So we have 8 plus 4 is 12, plus another 12 is 24, plus 10 is 34 marbles. So the probability of getting a green marble is something out of 34. Now how many desirable, at least for now, outcomes would there be? Well, that's the number of green marbles, which they said was 8. So 8 out of 34. And it's up to you, but you could reduce this now if you wanted to. You'll have to do it later if you don't. So this could reduce to 4 out of 17. Okay, so this is the probability that we do get a green marble. But now the question wanted to know the probability that we don't. So to get that, we just have to subtract this fraction from 1. So probability of not green is just going to be 1 minus 4/17. And since 1 could be written as 17 over 17, this is really just going to be 17 minus 4, which is 13 over 17. On this problem, we've rolled a 6-sided die 60 times, put the results in the table here, and we want the experimental probability of rolling a 2. So experimental probability, to find that, unlike theoretical probability, you're not going on what could happen, you're going based off of what already did happen. So we need to take the total number of desirable outcomes, which in this case was rolling a 2, and divide that by the number of actual trials, the number of times we tried to roll a 2. So in this case, our probability of rolling a 2, our denominator, our total outcomes, is going to be the 60 times that we actually did this experiment. And the desirable outcomes is just going to be how many times we succeeded in rolling a 2. So successes over tries. In this case, looking at the table, that was 14. So 14 over 60, which we can then reduce. Let's see, can at least reduce it by 2. That comes down to 7 over 30. On this problem, we have a cooler with 11 bottles of sports drinks, 4 lemon lime, 3 orange, 4 fruit punch. We randomly grab a bottle, put the bottle back in the cooler, and then go again. And then both times we want to know what's the probability we get a lemon lime drink. So first thing we're going to do before we find the probability, we're going to decide if these are independent or dependent events. And the two events are you picking a bottle and then picking another bottle. So to figure out which one of these it is, we have to ask, does the first event affect the second event? Does what I pick the first time around change what I'm able to pick or how many things I can choose from the second time around? If the events have nothing to do with each other, so that the second event basically is just starting over, resetting the whole situation, then we have independent events. If one event does affect what you can get the second time around, then we have dependent events. Now in this case, the key here is that after you grab that bottle, you're putting it back in the cooler. So you're not actually changing the sample space that you have to choose from on that second event. So these would be considered independent events. So now actually finding the probability, let's take them one at a time. So we want to figure out probability of lemon followed by lemon or lemon lime, whatever. So the probability of that first lemon drink, our total number of bottles to choose from, our total outcomes, we've got, let's see here, they said 11 bottles. So it's going to be something over 11. And then how many of those were desirable outcomes? Well, we had 4 lemon lime flavored bottles. So that's 4. And now we're going to multiply that by the probability of getting lemon lime again. Now, because these are independent events, when I put that bottle back, I now still have 11 bottles to choose from. So my denominator doesn't change. And again, I put the bottle back, so I also still have 4 lemon lime bottles that I could come up with. So the numerator doesn't change. And then we just reduce if we can and multiply across. So 4 times 4 is going to give us 16, and 11 times 11, that's 121. So 16 1/21ths is our probability of lemon lime both times around. For this situation, we want to know independent versus dependent and then the probability. So here we have 8 nickels and 6 dimes in a pocket. We randomly pick a coin and then place it on a counter, not back in your pocket. And then you pick another coin. So this situation, because what you're doing the first time is you're taking a coin out of your pocket, so you're taking it out of consideration for that second event, this is going to be an example of dependent events. Whatever coin you pick the first time and put on the counter, you're not going to be able to get that coin the second time around, so you're changing the experiment. Now, the probability they want is that both coins are nickels. So let's start by writing out what we're doing here. We want the probability of nickel followed by nickel. And then the probability of getting that first nickel, well, our total possible outcomes, the number of coins in the pocket, 8 plus 6 is 14, so that's our denominator for that first one. And the desirable outcomes, that's going to be the 8 nickels. So there's our probability of that first nickel. Now, once you take that first nickel out of your pocket and put it on the counter, you've changed the sample space. You no longer have 14 coins. Now you're down to 13 coins that you can choose from. And because you took a nickel specifically out of your pocket for this first event, that means you have 1 less nickel that you could get the second time around if you succeeded the first time. So now instead of 8 nickels, you're down to 7 for that second probability. And then we can reduce this a little bit. 7 and 14, that reduces to 1 over 2. And then the 8 and the 2 actually can reduce. That gives us a 4 in the numerator. So multiplying whatever's left here, we have a 4 over, well, all that's left down there is 13. For this set of problems here, we've got some events that are joined together by the word or. So for this one, we have a bag containing 5 marbles that are red, 4 blue, 4 yellow, and we randomly pick one. We want to know probability the marble is red or blue. So whenever you have one of these ors, you're going to be adding probabilities together. When you have one event followed by another, then you're multiplying. But these events, we were asking for either of these to happen, and it's just one experiment, just one pick with 2 different desirable outcomes. So in these cases, we add. So if we're trying to figure out whether the events are disjoint, which is to say mutually exclusive, or overlapping, we look at these 2 events, picking red and picking blue, and we ask if there are events that would meet both of these criteria. If there are no events that fall into both of these categories, we say these are disjoint or mutually exclusive. If there are events that fall into both of these, we say there's some overlap, and we have to subtract some overlap when we actually write out the probabilities. So let's just go ahead with this problem and see what happens here. So because a marble can be red or blue but can't be both on this problem, there's no red-blue marbles listed here, we would say these are disjoint events. So what that means is that when we do write out our probabilities, we're just going to add them together. We don't have to worry about subtracting anything. So our probability then of red or blue, our total possibilities, we've got 5 plus 4 plus another 4. That's 13 that all of these are going to be over for a denominator. And probability of red specifically, there was 5 red marbles, so 5 out of 13. And to that we're going to add the probability of blue by itself. Since there were 4 blue marbles out of 13, that's 4/13. And again, we're adding those. And at this point, since there's no overlap to worry about, we just go ahead and add these up to get 9/13. For this situation, we have a box of chocolates with 7 milk chocolates and 5 dark chocolates. And they say, let's see, 2 of the milk chocolates and 4 of the dark ones have peanuts. So you randomly select and eat a chocolate, and it's a dark chocolate and has no peanuts. That's the probability we're looking for. All right, so first off, disjoint or overlapping. We're asking about dark chocolate or no peanuts. Are there some dark chocolates that don't have peanuts? Are there any members of the sample space here that belong to both of these groups? And well, let's go back and reread the problem. We said 4 of the dark chocolates have peanuts, and there were a total of 5 dark chocolates. So there are some dark chocolates that don't have peanuts, because not all of them had peanuts. So these are then overlapping events. There are some chocolates that belong to both of these groups. So to figure out this probability, first let's find the probability of getting a dark chocolate by itself, regardless of nuts. And that is, let's see here, we had 7 plus 5 is 12 overall for the sample space, and 5 of those were dark chocolates, so 5 over 12. Now how about the no peanut part of this? Well, let's just add up all the ones that had nuts and then subtract it from 12. We saw that 2 of the milk chocolates had peanuts, 4 of the dark chocolates, so that's a total of 6 that have peanuts. Since there was 12 chocolates, 12 minus 6 gives us 6 that do not have peanuts. So the probability of no peanuts is 6 over 12, and we're going to add that. All right, so here's where it gets a little tricky. We've got a probability for the dark chocolates. We have another probability that we're adding for the no peanuts, but some of these no peanuts are also dark chocolates, so we're double counting them right now. To fix that, we're just going to subtract the number that are in these 2 different groups. So how many dark chocolates have no peanuts? Well, we said this before. If 4 of the dark chocolates do have peanuts, and there was 7 total, that means 1 dark chocolate did not have peanuts. So we're going to subtract that 1 out of the 12 chocolates. All right, throwing this together, 5 plus 6 is 11, minus 1 is 10, so that's 10 over 12. And we can reduce that now to 5 over 6.